Good evening, all of you, and welcome to our workshop webinar today, Understanding Equinoxes and Solstices. So, the objective of giving this workshop webinar today is that we will be having one of our equinoxes, that is 23rd September tomorrow, and we are arranging some type of activity where actually we will be having physically students and public coming here and performing certain observations, certain recordings of data. So before we do that, we thought that we will give just a curtain raiser to the event and understand certain aspects of it. So today I am Jayan Ganguly, and with me is Mr. Vinay Kumar Dubey, who is the in charge curator and project coordinator of the center. And we both will be actually sharing our experiences and sharing our understanding of this event so that it becomes known. And it is actually an open event, and so you can always stop us anytime if you have any queries, or if you can, if you feel that you can ask at the end, then that is also fine. So we can complete the presentation and then we can take the questions from your side. So let us start, isn't it?
Yeah, definitely. We'll start. I urge everyone that if any questions is there, please type it in a chat box and all, so that we can also take those questions in our discussions and go through it. So it's a two-way kind of discussion, not me and Jayanji. It's about all of you also. So please feel free to ask anything on the topic of equinoxes and solstices today. So let's move that.
Let's move. So this is a very famous picture from our land here, the Calicut. You know that we both of us visit this place quite frequently. This is our south beach of Calicut, and you are seeing that the sky is somewhat actually. It seems like that sky is touching the sea waters, and sun is going to set, and you can see in the borderline between the sky and the water. So if we actually move forward, if you take the camera and pan it, you take a bigger panoramic view of this one. So you see the bigger perspective. You see that more area, the line actually the interface between the sky and the water, it has elongated. So what do you feel about? It is very beautiful, isn't it?
Yeah, actually, it's a nice beauty is there with the beach and all, but I think this color and all these things coming from the refraction of the light and sunlight and sun rays, right?
Yeah.
So that's why the beauty enhances and it gives a cool environment to us, right?
Yes. Yeah. So why we are showing you all these pictures is somewhat like that, to see as the sky and this one interface, and we see that there is a bigger and bigger interface as it moves on. So if you are standing in an open field, like a football ground, or in your school the open ground, or in your college the open ground, or in a big Maidan type of area, you will feel that the sky actually it meets the ground in a circle. Now, this is, I think, all of us might have experienced sometimes, because this is very important for astronomy. We call this as a horizon.
Yeah, that's true. Even I am excited about my shadow. We're standing in the Sunday, and finding my shadow is also going diminished, as in going elongated in the morning as well as in the noon. It is going to. But the point is that due to sun, I think so that is happening, right?
Yeah. That we will discuss today. That is the topic of discussion today, and so I hope that now people, all the viewers, are when we speak about a horizon, I think it is somewhat okay that we started with the beach and elongated. No, that forms our horizon. Yeah. So similarly, for example, in night time, we have our sky observation program in Calicut Planetarium, Regional Science Center, Planetarium Calicut, and or not only here, anywhere. If you just stand in a field and if you just see the sky, you feel that all the star, like a hemispherical bowl, it actually intersects the ground, and beautifully like a canopy of stars you see. In fact, in our planetarium also, it is inside the planetarium, you feel the same effect. No?
It's a clear effect. I can see every stars as well as constellation also.
Yeah.
Yeah, that's a zenith is also there.
Yes, 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 yes. So that is the horizon, and this circle, no, this spherical ball. This is very important. This is an illusion actually. If you move out from the Earth, if you zoom out from the Earth in a imaginary spaceship, something like of that sort, slowly this illusion will vanish. Means you will not have the horizon will be fading away. So it is just since you are on the Earth. So I think you means there was a video by one of our contemporaries in science museums who has developed the actually that power of 10. I think you have seen that some camera is moving out of the Earth, and you are seeing the various faces. So that is quite interesting. So this leads to a model, an abstract model in astronomy. This is called a celestial sphere, sphere of stars, Khagol in Hindi. And what is imagined by our modelers in the sense that theoretical construction of understanding the phenomena is that our meridian, this one is there, our horizon is there, and the sky above us, we are in the center, and the sky above us forms the canopy. And then somebody on the opposite side also we feel that there is a sky on the other side of the Earth, and the full thing. So how do you perceive? How do you think that? So you thought about it when you were young or something like that? When you were in school or in college, did you think that like that one? Means you can model the full sky. Means it is
yeah. You can imagine, because in books and textbooks we used to read that this horizon, pole star, and this zenith and all. So longitude, latitudes comes into the account. So it's all about imaginary lines. So there is a visualization that how these lines are being perceived that in the solar system, and how you can imagine that one. So standing there in front of the on a plane or on Earth, we can. I especially think about that longitude, latitude, where it can, and how it is going to coincide me, and how it relocate me at this position.
Yes.
So that's why relating is there.
Yes.
But that time I'm not able to visualize that one.
Yeah. So actually this model, this celestial sphere model, helps us in understanding various phenomena in astronomy. But for understanding, actually, for example, if you take a rectangular room and if you want to place an object in the room, we use our Cartesian coordinate system, XYZ system, or cylindrical coordinate system, or spherical coordinate, various types of coordinate system. So they are acting like a reference frame on which we locate our objects. So to make a precise observation, to make the quantization of the object, how it moves, what is the velocity with which it moves, or something like that, we have to actually construct certain framework in this model, in this abstraction, that is the celestial sphere. And there lies actually the concept of coordinates, what is coming up in the celestial sphere. So for any place framework, actually we require an origin and maybe a line of reference. For example, in Cartesian we have x and y coordinate, and where they intersect we have in two-dimensional we have the origin. Similarly, XYZ coordinates we have where they intersect we have the origin. So in this sphere, we are seeing a sphere, a Khagol, our sphere. So there are two types of circles possible in this. You can proceed. So if you take the plane of the circle, and if it you'll take a football or take a orange, for example, we slice it with a knife. Now what we see is that a circle is formed. The intersection of the plane and the sphere, a circle is formed. But then the circle size varies if you go on slicing. But at one time when you slice it to the center, you get a circle which is of maximum size. Beyond that size, actually, for that sphere, you can't get a circle. So that big circle, what we call is a great circle. It is termed as a great circle, and all other circles are small circles. So to keep standard for a particular sphere, we require great circles. So in this Khagol also, in the celestial sphere, we have to choose great circles and origin for making our things more precise. So I think this is one model. I think you can say that we have the topmost point. There are some definitions. So zenith is there, horizon we have already spoke, and we have something like when we see that approximately in some direction, which is the focus today. Actually, sun rises approximately from a certain band in one direction. So that full band actually we colloquially call it as eastern side. Though we have to precisely fix the direction. That is one thing which we will be discussing today. So as we see that sun rises in the east and sets in the west. What is that? Also, we will try to answer today while we model it out. And if you take a perpendicular bisector of that particular east-west line, we get the north-south line. So, and if you draw an imaginary circle through the north-south line, that in the Khagol, in the big Khagol, that is called the meridian. The meridian is quite important because any object which crosses the meridian, we say that it is a transit. So once it crosses and again it crosses, the interval between these two timings gives us certain durations, which are certain fixed. For example, moon transit is occurring, sun transit is occurring, star transit is occurring. I think in our observation also we have incorporated measurement of the transits. You are aware of all these things. So, so that is the thing. And zenith is the highest point. That is the topmost point in our
top of my head.
Yeah. So if we are standing, wherever we are standing, that is because Earth is very big. So our dimension is very small compared to the Earth. So we can consider ourselves as the center of that horizon, center of that great circle. And an imaginary line passing through us goes to the zenith. And that cuts the sky. That is the zenith. So that is the way actually the local sky is parameterized. Yeah. So now you can see then, as I was telling you, that we have certain great circles. The horizon is one of the great circles. You can take one point, say north point, as the origin. So if you measure the angular distance between the north point and say in this particular thing, you have a star here. If you take a perpendicular secondary, a great circle perpendicular to the horizon, that is secondary. And if you take this, so we have the altitude. So this is called the altitude, the angular separation between the horizon and the star. This is the altitude and this is the azimuth. So this, why we are speaking is that actually we want viewers to actually get a glimpse of how measurements are taken up, or what when we say altitude, isn't it? What do we mean actually? Altitude of a star, or altitude of sun, or altitude of a moon, or whatever it is. When we say altitude, what exactly we try to convey? So, do you have anything to add to it?
Altitude. That means we are measuring that thing in radians or degrees.
Yeah, degrees. Right? Because we can't measure linear, because that is very important in astronomy.
I think that earlier sextant and octant were used in this one.
Yes,
because we are right now using GPS. Our mobile phones are there and GPS, and from there we can give the altitude, latitude. But earlier that is even the octant, and then after that the sextants comes up.
And all they were using. Yeah.
So that thing, I think sextant is still in use.
We in our gallery, also astronomy gallery, we have that Ecobras section. We have a sextant that people can actually measure the angular separation between two objects. So that is also there. So now this is a very important diagram in the sense that, see, we have chosen one reference. Circle that is the horizon. That is the horizon, and now the one reference circle is okay, but there are certain limitations which we will not go in this program, because we are not teaching you coordinate system yet, but we are trying to introduce different reference circle. So one more reference circle which we will be repeatedly using is called ecliptic. Now, what is an ecliptic? Now, see, in this picture, you are seeing that the sun is there and Earth is moving around it. So do you like to explain how actually the ecliptic is formed? Do you like to say?
There are two things, I think, celestial as well as the ecliptic, right?
Yeah.
This ecliptic is the rotations of the sun.
Means projected image rotates in a great circle among the zodiacal constellations. Some constellations that is means all constellations have fixed position, but some constellations which it traces. So that we call zodiacal constellation.
That means that's the opposite. That is
Earth is moving and it is projecting. That is the reason actually, ancient Indians classified sun as a planet. Now, why they classified? They thought that anything which moves in the sky is a planet. So that is the reason the moon was considered as a planet. Nodes were Rahu Ketu was considered as a planet. Sun was considered because sun, they saw that they were very keen observers. So what they saw is that certain constellations were visible in certain months and were absent in some other months. Then by the logic, they found out that see if this thing is happening, what happens is that if those constellations which are not visible here, they are in opposite side, and they are present in the morning time. And since the sun's light is dominating the sky, we can't see those constellations. So sun is actually moving among those constellations. So that apparent path, this one, the projected path, this is very important, and this is called the ecliptic. In astronomy, we call it as ecliptic, and that is the projected image, and that is one of the great circles which will be chosen as a reference circle for our one of the celestial coordinate system, which is called ecliptic coordinate system, mostly used for studying sun and planetary systems.
So by denoting this constellations where the projected line there with respect to sun, that we can say that the sun is also moving, right?
Yeah, that is the way actually our ancient people classified sun. But their definition was something like it is more fuzzy, and they saw that something which is wandering. But today's definition or a modern definition of sun and planets are quite different. So that today we know what is what. So that was the thing. So with this, actually, this is one more way of representing ecliptic. How do we? So you can see that the equator, celestial equator, is the equator is a line on our Earth, which divides the Earth into two equal halves. Halves are always equal. Two halves, I can say. So if you extend that plane of the equator, it intersects the sky in a certain great circle, because it is passing through the center and Earth is in the center. So that is also a great circle. So that is the celestial equator, and we have the ecliptic, as we have discussed. Now these two intersect at one point. It is called as a vernal equinox. And the vernal equinox, if an object is in the vernal equinox, actually it is present in the celestial equator also, and also in the path of the sun. So that is called equinox. And today's program is focusing on equinox and solstices. So we start the journey somewhat from here itself. So that is the equinox, and 6 months away from here, that is on the other side, we have the autumnal equinox. So we have vernal equinox, autumnal equinox, and then we have the actually this one what we are having tomorrow is the autumnal equinox. Okay, so vernal equinox is on March 20 or 20. So now, and one more thing we are saying, that why there is a inclination between this ecliptic and the celestial equator. Do you like to throw some light on it?
I think so, that because celestial equator is just projected line, that is tilted angle, right? That is about 23.5 or 4.
Earth's axis is tilted.
So it's actually vary from 22 to 25 something like that. Right now it may be 23.45 or 5 something like that. So that is actually equator. When I expand the equator in a outer way, then I will get that celestial equator. Right? And this path, ecliptic path, is that the plane path that is taken as a sun as a reference. So at this path, I think so, vernal equinox and this one, the sun is also in the same plane with respect to the tilting angle.
Yes.
So it's like the sun rays will be something perpendicular to the.
Yes, exactly. We will come back to it. That is a very important point. We will come to that. We will be coming in that. So basically, this angle between this celestial equator and the ecliptic, this angle is equal to the inclination of the Earth, because the way we have defined it, and this is known as the obliquity of the ecliptic. Technically, but if you want to say, it is known as the obliquity of the ecliptic. So we have the obliquity of the ecliptic, and this is the way actually, and this also forms this vernal, means that first point of Aries and the celestial equator or the ecliptic, they forms actually separate frames of reference. So we have one frame of reference like azimum is our north point and the horizon.
My laptop won't connect. You can only choose. See.
Please mute. We will have question answer session in the end. So now we are discussing. So I think you mute it. So what we were discussing is that, see, we have different frames of reference because we require those. and as we have already discussed that. Now, one more thing, did you notice that, see, from Calicut or from anywhere in Calcutta or Kanpur or wherever, the sun rises, but every day it doesn't rises in the same point. Did you notice
yeah.
that?
Yeah. In the different months, it will come in the some different.
But it doesn't move very far away.
Very far. Yeah.
They are in a certain band. It expands and it decreases.
Is there any meaning about that one?
Yeah, because we spoke about the obliquity of the ecliptic. Yes, sir. So everywhere, actually, every day, only on those 2 days, that is on 20th March and 23rd September, sun is actually on the. It is always on the equator, as well as we will come back to those specific diagrams as we move through. So it is exactly on that. So that it is rising in the exact east and setting in the exact west. But on other days, it is on some other point of the ecliptic. Yeah. So it is not the angular separation increases, and it increases until actually we reach the maximum angular separation of 23 degree 27 minutes. Okay, so that is the variation. That variation is seen throughout the year from all the locations.
Okay, so that means sun is going this 23.5 degree north as well as in south.
Yes.
Not far.
So one leads to solar solstice, that is on 21st June.
Right.
We have the longest day in the year, and one we have on the winter solstice, that is on 22nd December. We have it on the longest night in the year. So these are actually have maximum separation. So that is one reason you can see in this picture. There are 2 imaginary lines, traces drawn, showing the movement of the sun, one on 21st June and one on 21st December. So you can see that there is a band varying. The altitude of the sun is different in these two. Actually, the altitude is high when it is on 21st June, and this has an implication that we will discuss today. Tomorrow's activity involves all this. So that is high, and other one is low. So I think this is fine. So now let us go back and again look at, because we are focusing on this model because we want our viewers to get a idea about the abstraction involved when they study astronomy and do measurements. Because without this is the corridor in astronomy. Whatever you study, galaxies, black holes, nebulas, but everybody has to study these, because first we are staying on Earth and we are observing from Earth. So sun, moon, things, these stars, these are our basic things.
Right.
Then comes galactic, extragalactic, and radio and all those things. So this is the corridor with which whenever a person wants to learn about astronomy, they have to pass through, they have to understand, because the quantization starts in astronomy with this model. Okay. So we have see, this is a equator. This is if you are located in the equator. Okay. So you are located here. So the pole star, what is the pole star? We will come to next slide. It is a star which is located along the rotational axis of the Earth. So that from a location, for example, in everywhere, the pole star's altitude, that is separation from the horizon, is fixed. The Calicut, it is 11.15 degree. It is in north. Because pole star, one thing is that, so we say pole star, but actually it is a generic word. What we say is that actually it is for the northern hemisphere, and most of the people live in the northern hemisphere. And we have a good means we have a correct star which is along the axis of rotation of the Earth. So actually in the northern hemisphere we have a pole star. Though we don't have like that exact pole star in the southern hemisphere, and people are also left. Only Australian people are there, and Antarctica over these days. So, but there one star is there which is called Sigma Octandis. So that is that can be treated as a pole star in the southern. But that is not taken into consideration. When we say pole star, it means north pole. And if you are on the poles, actually pole star, your pole star is in the vertical. So altitude will be 90 degrees. So everything, all the stars, actually they rotate parallel. All these stars rotate parallel to the horizon. Even sun, if in course of a year, it makes a spiral. It goes up in a band of 23 degrees 27 minutes. It goes up and comes down. So whenever it is above the horizon, you have 6 months day, and then you have 6 months night. So that is quite interesting, and the motion of the stars is quite interesting there. So we have the celestial equator, celestial sphere, and we have spoken about the motions. And this is one more very interesting thing. See, um, everything is rising, everything is setting. So that is. So how do you visualize this? So one important way is good is that we take a camera. We take a camera, our DSLR camera, or means shutter open. We can keep timer and keep it open. Or previously we had films, we keep it open. So we focus it towards the pole star and keep it open. Then after certain duration of time we can close it. So we see during the duration of time stars, they will leave some star trails, some circular lines, and we can actually measure the duration of for which the shutter was open, by how long, because earth rotates fully in 24 hours. So from there actually we can get the duration, but that is a different aspect. But one thing is that we can get star trails, and this is a picture of that. So this we kept it for that. Now this, would you like to comment on this this particular slide? So, for example, it says about certain stars are always seen in the sky. So those stars, no, they are never setting. So what is rising and setting? When they move above the horizon, it is rising. When they move below the horizon, it is setting. So there are certain objects which never moves above the horizon. Like you can see that this particular object, it never moves above the horizon. So it is always below. So that can't be seen from the other areas, not in that latitude. So that is there, and some we will not set. For example, in our Calicut, since our altitude of the pole star is 11.15, we will come back to this discussion again when we move. There are some stars whose altitudes are less than 11.5. They will be acting as pole stars. Other stars will set. So that is quite interesting. And our sun also, it rises and sets. So what is rising and setting is very important. It moves above the horizon. We say that it has a horizon. But then it is just moving above the horizon. There are certain errors, like a refraction is there. Actually, it is not above the horizon, but still appears to be above the horizon. Then there are other sources of errors also that we will not discuss just now. Now we have moved to poles. Now we have moving to the we have seen in poles, we have seen in equator, we have already shown something, but this is a more abstract, more quantized drawing showing how actually the stars and other things moves when we are on the equator. So if they appear vertically straight, they will move straight and they will come back. So it is the motion is, so these all we can simulate very well inside the planetarium, because the machine allows us to move any part of the sky. You can go to North Pole or equator or intermediate anywhere. So that is quite good. And so that is one thing. So this was something which says about pole star. So pole star, Dhruva Nakshatra, that is not a constant. The same star is not there for,
it is also moving.
Because why it is moving is quite, see, from this animation we can understand. What happens is that see, I said that we can have a star along the rotational axis of the Earth, that is called. But if the rotational axis changes its direction, so another star which is on the rotational axis becomes the pole star. And it is changing at around 54 arc seconds. So 26,000 years it takes to make a complete circle. So it is changing, but it is not noticeable because the angle is very small.
It's a oblong kind of.
So and it wobbles also, as you were saying, that due to precision and nutation, that is due to all these effects are there because of tidal motion, loss in energy, and all those things. So that is the concept of pole star. Now this is a very important thing, very important concept which we will be using for our discussion today. See, from any place, if you know if you are in a place where actually you have knowledge about stars, you know some stars, and you observe that some stars never set. One of the stars, especially, it never. Every star is rotating about that particular star. It appears, so that is the pole star. So with that knowledge, can you know that where you are located? Or, for example, if you are lost somewhere in a jungle or somewhere in an isolated area where your GPS and everything fails, no connectivity, no internet. So how do you come out? So there actually what happens? You can.
No, I don't know, but what exactly? Maybe sextant can be used, or some tools can be used, or can we put some Gnomon kind of thing and measuring the latitude.
Yeah, exactly. What see, this diagram actually answers that question. So as we said, that's for each observer on the Earth, we can draw a celestial sphere for that particular observer. Now, what is the latitude of a place? Now, we have studied in our school in geography. Our geography teachers taught us that latitude of the place is actually the angular separation from the equator, plane of the equator, and where our place is there. If you draw a radius of the Earth, how much angle? So that is the latitude of the place. Now, geometrically, it can be easily proved from this diagram, but we will not go into mathematics just now. So it can be proved that altitude of the pole star, for example, this angle is equal to the latitude of the place of observation. So these two are equal. Actually, this is a 90 degrees. So yeah, any question?
Yes, actually, I couldn't understand much. Like the solstices and equinoxes, like I couldn't understand them, and this I couldn't understand. Like what is the relation?
Yeah. So anyway, you concentrate on this relation which we are speaking now. We will come back to solstice equinoxes again in future slides, and then again we will see at last whether you understood or not. Because concentrate on this picture. This is quite interesting in the sense that, as we said, that for any place you see that the zenith is the vertical. Means if you are standing here, if you are observer here, one line passing through your sky, through your head and going to the sky, this is actually the zenith. Now the pole star is here, and this angle is the altitude of the pole star. But this north and zenith, this angle is 90 degrees. So what is this angle? This angle is 90 degree minus this particular latitude, means altitude of the pole star. Again, you see that these two, if you know high school geometry, the latitude and this angle, that is the zenith's altitude above the horizon, they are equal because they are the corresponding angles. So this is a parallel line, these are parallel line, this is a transversal, they are corresponding angle. And again, the angle, this celestial north pole and the celestial equator, this whole thing is 90 degree. And so what happens is that this is the common. So these two becomes equal. So when these two become equal, yeah.
I actually don't know anything much about high school because I'm in 5th standard.
Yeah, then you try to understand, because I can't help you because you have to study something. But you can listen, you can see the slides, I think. No, you can get through it, some sense, you will understand.
Jan, do you identify the pole star?
Yeah.
Ever in the sky?
Yeah, what he's asking is that did you ever saw the pole? From where you are actually? From
Sir, I'm right in Mumbai.
You are in Mumbai. So from Mumbai sky, did you see the pole star anytime?
Not from Mumbai, sir. I went in the outskirts, so I actually saw the Big Dipper. So then I used that to locate the pole star.
Yeah. So that is good that you located the pole star. Now, actually, from that ground to pole star, there is an angle, isn't it? The pole star is at a certain angle. So
yes, sir.
Yeah, so that is the altitude of the pole star. True. So if you somehow measure with some instruments or some angular divider or something you use, or your fingers if you use on palm top, you can measure the angular separation from the ground to that pole star. Then you know where you are, in what latitude you are. That is the beauty of this result. Now, by measuring the altitude of the pole star,
that means Jan can measure the latitude of his place by identifying the pole star and denoting from
measuring the angular separation. So that is one of the very classical results.
Okay, so then he can also check it from the GPS.
Yeah, GPS also you can check it. So that I think you should try since you are in Mumbai outskirts. You locate, and you have already located the pole star. You try to measure.
Sir,
yeah.
I'm not in Mumbai outskirts. I'm living in the heart of Mumbai, but I just went for a trip to the outskirts, so I just saw it.
Good.
But right here, there's lot of light pollution and all of that.
Okay. So maybe next time when you go to outskirts, you can do this activity and you can check this result. Okay, that I think you should do. Fine. So let us move forward. Now, this is all of us know that this Earth revolves around the sun, and as it
axis.
revolves, as its axis is tilted, you can see that during these two regions we have more sunlight. So it is we have this when it is exactly far away, farthest from the sun, and it is, the tilt is towards the sun, we have more sunlight, and that is that particular day on which actually this happens. That is called the summer solstice, and that actually occurs on 21st June. That is somewhat fixed because the orbit of the Earth is not very rapidly, though it changes, but it is somewhat constant on a very long period of time. Similarly, when Earth is on the 6 months later, when Earth is on the other side where the inclination is away from the sun, we have very long nights. So we have summer solstice and winter solstice, and they are at the separation between the sun and the position of the sun on the ecliptic and the celestial equator is maximum. That is 23 degree 27 minutes. So
that means in June solstice we can get more light, right?
You longest day, longest day, and we have the longest night. But then there are other positions where actually in between the solstice, that is June and December, we have two other positions 3 months apart. From June solstice, if you go now September, now. So at this 23rd September, what happens is that the rays of sun falls vertically. It appears to fall vertically along the equator. So when the rays are falling vertically along the equator, you will see that at that particular thing that we say something called as a local noon. Local noon is the time where actually, as per the local time, the sun is at its highest position. Though sun appears at the highest position, but sun is not rising in exact east on all the days that we have been discussing up till now, and we will again show you. So that day it rises exact east and sets in exact west. And
Sir, actually the sun rises in the exact east only on 2 days in the full year.
Yes, that's what we are telling you. That on March 20th and September 23rd, it does goes to this. That is the reason it is called equinox. That is equal day and equal night. So that is the reason it is. So you can see in this slide also show you. This slide also.
Sir, so the equinoxes is where the sun rises in exact east. So those are the only two equinoxes where it's at the highest point. That's why we get the shortest shadow or
you could not at the highest point. Highest point occurs. The thing is that when it reaches the sun on its diurnal rotation motion along our sky, it reaches the highest point at all the days. But every day sun doesn't rises in the east, as we have seen. Why?
So exact east is only on the two equinoxes.
Yes, correct. You are correct.
And when it reaches its highest point, it's like the shortest shadow.
Yes. That is also
like the shortest shadow of the full year.
Yes, that we will see. Whose shadow is there, that we will come to it. So you see this particular slide, it shows how on these two solstices actually the rays are vertical. Now this is one more, as he was telling, that it shows the duration, which is actually means in the southern side, the sun's apparent path, the sun's diurnal motion, what I will say, is inclined in various ways depending on the dates on which we are observing. Okay. So this is for Calicut. For example, Calicut, the pole star is latitude is 11.15. The pole star, though it is not drawn in scale, it is written there. This diagram is not on scale. So at 11 point, the pole star is at a height of 11.5. So we see that the equinox and that the solstices, how the angular separation varies during the other days, that can be seen here. So these are some of the graphics which shows actually how
this is the path of the sun.
During the solstice and during the equinox, you can see that though they are moving on the sun, apparent the beauty is that the apparent sun, the sun actually moves on the ecliptic. But one thing is that, see, when sun is on, say, 23rd December, sun is on 23rd December on the ecliptic. Now we have the rotation of the earth, that is the diurnal motion of the earth. So sun will make a small circle. It will no more make. So these are all small circles which are formed. And when it is on the exactly on the east, that is on the equinox, sun is on the ecliptic, it is traversing along the greater big circle. A great circle, what is called. So that is these are the two things. So this is one more depiction,
Sir,
same picture. Yeah,
so one more question. Can you go
yeah,
to the previous slide?
yes, yeah.
It's like
Tell
based
me.
upon.
Yeah, tell me.
So actually, like, is it that the day is shorter in the winter solstice and the day is longer in the
Yes,
summer
yes,
solstice?
correct.
Because in maths it is said that in circles, if the radius is smaller, it goes faster. So like the
Yes,
sun is going in a like sort of circle, so the radius is smaller
yeah,
because
yeah.
in the
Because
diagram for the winter solstice, so it goes faster. So then the day
yes,
becomes shorter.
you can see from this diagram itself, no, the amount of time the sun is above the horizon is less than what it is here. It is here for more time, so that naturally the day is shortest
Right.
during the winter.
So
So
you can actually connect it with that maths principle that if the radius is shorter, you can go faster around.
yes, yes, you can.
Yeah, you're correct.
You can do that. So now tomorrow, no, this we are going to do some activities. The setup is quite simple, and you know that very simple. We have to have a flat ground, and we have to arrange one pole. I think we are arranging a lot of poles in our center. So we are expecting also a lot of people will come, and a lot of people will do maintaining all the protocols of COVID.
Right, yeah.
Yes. So we are seeing that the pole is creating a shadow. Now let us see. Now let us see this diagram. This is quite this one. It shows that the correlation between shadow length, and she was speaking about that shadow length and all those things. So
Right.
that if you take the pole and if the sun rays are falling, now it falls and a shadow is falling. So here you can see the sun rays are falling of the pole, and it
Right,
falls the
yeah,
shadow
yeah,
here.
shadow.
And you see that if it is falling this exactly straight on the equator, the rays are parallel to the equator. So what happens is that from simple geometry, you see that this ray is coming here, and this is the line of the equator, and these are the you can see that these angles are matching. So in that way, actually, we can do certain observations. So this is one of the figures, and you can see the other figure here. The sun is there, how the shadows fall, and as the sun moves across the sky, the length of the shadow will vary because it will cast different shadows in different direction. For example, here in this figure is quite interesting. For example, in the this one, the highest position, we said that we have in the summer solstice. Sun is on the higher, so its shadow will be small. In the winter solstice, sun is at a lower this one altitude, so the shadow will be longer. Equinoxes, it will be in the this
middle
one,
of that
in the middle of that one. Though every day the shadow is shortest when the sun is at the highest position in our sky, but then equinox day actually it will be the shortest. And what is the most important thing in the equinox day is that, as we have seen in the previous slide, the angle of the angle, if you see the setup. For example, I think in the next slide itself we have the setup. Here we will show you the setup. So let us keep this figure. So if you have the shadow at if you mark each time, you are marking the shadows, and anybody can do it. Now I think in the terrace also they can do it. You need not go to any science center or planetarium or anywhere. You can make your own setup in your terrace and do it, but do it under certain guidance so that you can measure it. Keep a team, not alone. Maybe your parents or your brothers, sisters. To take time. So you have to do it from morning to evening judiciously. We'll show you how to measure and all those things. So what you have to do is that you have to go on each time. No, so the procedure is somewhat like this. You have to keep a pole on a plane surface. How do you see that the surface is plane? If you have a spirit level, I think if you can keep, and you'll see that the spirit level is same, or somehow with a plumb line you can make it see that. And you should have a vertical pole. And no, this vertical plane, the sundials and all those things. In technically, we call this as a gnomon. So gnomon is there. And then you should know the latitude, because we are going to measure certain things to confirm whether actually equinox is on 23rd September. So you should have a pre-knowledge about the latitude instead of actually waiting. You can have previous day night, you can do all those activity, but otherwise also with electronic gadgets or some charts or somewhere, you can actually come to know about your latitude of the internet or mobile app. You can come to know the latitude of the place. So but now what you have to do, what are the steps you have to do? You get up early in the morning, very early, maybe before sunrise. If you get up, that is good. And if you can see the horizon very clearly from the top of your building, or from the ground from which you're watching without any trees or like that. If you get a location, that is very fantastic. And if you can see the sun rising, no, and you have the pole, vertical pole somewhere, you put a chalk, take a chalk, put a line along the direction of the not shadow, along the direction where sun has actually is coming up. Okay, along the direction. Do that.
So we are fixing that when sun is
coming up. Yeah. And at what time? You write in your bracket.
So rising.
Rising. You just put a line in along that direction and write down what time it is rising. And then actually you start. You already know what is the vertical height of the pole, Glomon, what you have already. Then every 10 minutes from that time, this activity is a bit involved from the part of the group. So it is advisable not to do single-handedly because you will get tired, fatigue, and all those things.
Yeah.
So a group of 4 or 5 or 6 will be good enough, and all of you can share. For 1 hour, somebody can do. For another 1 hour, second person. So everybody will be enjoying. So every 10 minutes, what you have to do is that you have to take the chalk piece and make a this one, make the direction of the, so that vertical line, no, that it will form a shadow. So the length of the shadow you have to measure. So instead of each time measuring with a scale, you from the base where the shadow is actually ending, you put a cross and put the time there. So you do it for the
time and the length of the shadow.
Length of the shadow, you can take it afterwards also. Okay. So you measure that and you continue that. Then at when the sun is at the highest point. Okay. Somebody unmute your mic. You can whistle in your home afterwards. So please cooperate. Somebody is whistling there. So I think that is fine. So now, again, when the sun is at the highest point, actually that time you have to see, you have to shadow a shortest one. So that is very important. That you should record. And that you should go on doing. And when you go up till some more time, you go on doing, and actually it is ideal that you do it up till sunset or beyond that.
Yeah.
Beyond that means after sunset there is nothing to record, but you know the direction in which actually sun has set and what is the time. So what happens is that you get the different orientation of the lines, different length of the lines, and the times. Now once you get the this one, no, our shortest direction, that is along, since the vertical rays are vertical to the equator, it is along north-south direction.
True.
So once you make a perpendicular bisector of that particular line passing through the Glomon, that is the pole, it will be, if it is along the direction of the sunrise and sunset, if your calibration is pakka, then actually that is the one of the tests confirm that your sun has exactly risen in the east and set in the west. That is one thing. Second one thing you can test is that that angle you can measure the angle of the pole. You know the length of the pole, length of the shortest shadow. Now you know that there is one trigonometric ratio is there, tan theta. Tan theta is in a right angle triangle opposite by base. That is tan theta. So if you measure and if that angle turns out to be the latitude, or if you measure in whichever way you measure, co-latitude or latitude, so you get a confirmation that actually that is matching. These two are matching. So these two, if it matches, that is you are sure that actually what happens is that it is an equinox day. So, and also if you get the sunrise and sunset time, if you record it, if you see that it is approximately, if you without errors and all, if you have with minute errors, if it is approximately equal to close to 12 hours, that is also one more confirmation. So those things you can do, and you can make an observation sheet, like you can write the date of observation. What I have written for only 4 observers, you can go on increasing up to 5 or 6. You can write the pin code so that people understand that the email address, latitude of the place, longitude of the place, and you can actually put the shadow times at each, starting from 6 o'clock, 6:10, then sunrise time. You can just, if there is no shadow, since if sun is not there, there is no shadow. So you need not write. You just put a dash there, but you start from a little beginning so that you know what is the sunrise time. That's the reason we have started, and then you can go on. Link given by Astronomical Society's Public Outreach and Education Committee. You can see this link. You can note down also this link. So they have a form, Google form uploaded, and whatever you're writing, You just put your details there and you upload it in that. So they also get the data. So it is actually a national event they are doing. That is, they are doing it from Kashmir to Kanyakumari. Everybody is getting involved in this project. So you also, all of you are urged to do that also. We will be also doing that for the physically those who are coming here, we will do that. We will have physical data as well as digital data in these forms. And I think it will be really a grand festive. We hope, if there is no rain, if the sky is clear. What do you feel? What do you feel about that?
I think that's a great that people actually putting their numericals and calculations there on the seat and the plane of the earth.
In fact, they can plot, as you rightly said, time and the shadow length. They can plot and they will get a good curve out of it, a conic curve.
Because after 15 or 10 minutes interval, they are noting down everything. So it's about 12 hours. It considers 70 or 60 kinds of plotting number. They will get it plot. That will be the nice one, and it will be a great practice for the students also. That
they can do it as a project also for their school or college.
Learning which is matching with the practical.
It is a confirmation. It is an astronomical experiment. So I think we are done. We have given an overview of what is solstice, what is equinox, and tomorrow's activity, which we will be doing here, or which you can actually try in your own location, wherever you are located, and continue that. So I think you have anything to add?
Nothing. I'm thinking that this solstice happened, but what happened in the poles? Whether that in the poles that sun is actually not. It's not set, right? It's happened for the entire 24 hours, something like that.
Yes. So that's quite interesting.
Even in the midnight also sun is there.
Yeah, in fact, we are having a functional astronomy club here, and there was Mr. Abu Bakr. He visited Norway or somewhere. He stayed there, so he used to tell that night 12 o'clock the sun is up, but people are sleeping. Now, for carrying out the civic life, they used to make arrangements on that. So that is quite interesting.
But in northern hemisphere, I think so. That exercise can give us a clue.
Yes. So now let us keep it open for public participant discussion. If you have any queries, you can ask us. Anybody.
So is the equinox actually the time when the suns are exactly parallel to the equator?
It is the time when actually what happens is that equinox normally said to be the day. The day on which actually it rises, and you can confirm it by measuring it in when the shadow is shortest. So because shadow lengths vary, and at that time when actually the sun is in the highest position, the shadow will be shortest. And if that angle, as we have explained you, it matches with the latitude of the place, that gives a confirmation. That is the way.
There is no declination of the sun.
Okay, sir.
Okay, fine. Any other questions? I think in chat box also you can put. I think it was full screen share was fully done. We were also observing from here, so I think that is fine. Anybody else with something? Choose spotlight mode today. Okay. Anyway, I think that we will do it afterwards, so that is over.
Okay, so tomorrow we'll put all the thing on the table and get it done. That's ready and all these things.
Yes. And if
I wanted to ask something about the zero shadow day. So does the zero shadow day occur on tomorrow?
No. Zero shadow day is different. Zero shadow day is actually the day actually when what happens is that sun is exactly overhead of you. See, every day the sun is in the highest point. We never said that the sun is in overhead of you. Okay, overhead means your shadow will be, there will be no shadow. That is the reason it is called zero shadow. If you keep a circular pipe, a small pipe, you will just, if you keep it above a glass plate, you will just see a circle. You will not see any breadth or any third dimension. You will see the two-dimensional circle. So that is the thing, that if you stand, you will just see the shadow on your foot falling during that time when actually the sun is in the highest position. So that is
sir, does it happen on the summer solstice?
No, it doesn't happen on the summer solstice. There are specific to the latitude of your place, provided your place of observation is between Tropic of Cancer and Tropic of Capricorn. If you are located somewhere in between, you will get a day in a year where actually when this particular thing event occurs, that your shadow, the sun is at the exactly in the zenith point.
Yeah, I think that when this thing's equinox is there,
Yeah.
so on the equator that is a zero shadow.
Yes, yes, yes.
For the equator, people who are there in the equator,
Yeah.
for them that is a zero shadow.
Yes, yes.
Because that is already perpendicular to that. Sun is directly perpendicular on the equator.
Yeah. So I think if there is no other question, we can expect a good measurement tomorrow, and we can conclude this session. I thank all the viewers who have come and joined us for today's program. Thank you, all of you, and keep in touch with us.
Yeah,
Okay?
yeah. And keep measuring tomorrow what's going on for the equinox.
Okay.
Thank you all.